Let's see. I would like to review our notes a little bit. I would also like to introduce the new homework assignment. So let me start with that. Homework 3. All right, so homework 3, due not this Sunday, but next. Might have to push that back a little bit depending on how it goes for you. Have 3 problems. These are all correlated data problems. So that's the theme right now that we're in, is correlated data regression in particular. Let's learn how to do regression models that we're more comfortable with now, but now allowing for the residual terms to have correlation within them. Most of the examples we're going to see are correlated because of repeated measures over time. So we'll see, I think all 3 of these examples are longitudinal data. Just FYI, there's different jargon that can speak to measurements over time. Biostatistics, we usually have longitudinal data. There's also time series data. And they are both basically the same thing, repeated measurements over time. Usually time series is reserved for longer relationships. So weekly measurements for 10 years or something like that. Whereas a longitudinal study typically has more replicates, more individuals measured at relatively small numbers of time points. Longitudinal studies are valuable when the interest is in assessing changes over time. What is the profile over time of a response variable? And when we do regression, we get to see what's the effect over time of a covariate. The first data set you're going to play with is in this package that you might have to install. But once you have it installed, let me show you how to get the data. Okay, I already have NLME on this computer. When you library in this package, NLME, you have access to this built-in data set called orthodont. You can access orthodont by saying data orthodont. Now, there is a data frame called orthodont. Let's take a peek at it. So for each of 27 people, we have time course data. So the main response variable is this distance, which is, I can't remember the details. Let's look at the help file. Question mark orthodont. For built-in data sets that come with a package, they will tend to have help files that give you documentation and what the variables mean. So the response, these are orthodontic measurements over time for several young subjects. Distance is a numeric vector of distances from 2 places that I won't try to pronounce. So a response variable for our purposes. Then we have, as covariates, we have age and gender. age is in years. Because we have correlated data, another variable that needs to be in our data set is some way of identifying repeated measures on the same person. So in our orthodont data set, we have the first 4 rows are all the same person. I know that by the subject column. Subject or ID or some kind of unique identifier for this person, M01. Then we have M02, and we will eventually have F01, F02, and so on. And for each one of these people, we have 4 measurements. First individual was measured at ages 8, 10, 12, 14. Let's table age to see if it's the same for everyone. So I'll do table age. Every person was measured at the same 4 ages, 8, 10, 12, 14. Yeah. All right, so for these data, do some exploratory stuff first. That's my recommended first step when you have a data set, is look at it. Do exploratory things. So I'm going to ask you to do some side-by-side box plots, distance by time, and by, when I said time, what I really meant was age. So by time, I mean age. Show me side-by-side box plots of distance by time, and give me a picture for males and a separate picture for females. Then comment. What do they tell you? Also make what are called spaghetti plots. And all a spaghetti plot is in the orthodont case, we could plot age, and then for each individual, we could show a connected line segment. There's one individual. Here's another one. And here's another one. So if you did that for all n individuals, it looks like you dropped a handful of spaghetti on your plot. That's where the name spaghetti plot comes from. When you make a picture like this, it's a quick visual of what's happening over time, what's tending to happen over time. Sometimes they're more informative than others. In your homework, the orthodont picture is fairly easy to interpret and visualize. I think the schizophrenia one is not so much, because there's too many individuals. So if you just have a relatively small number of individuals, this kind of picture is handy. If you have a few hundred individuals, you end up with this mess where you can't really see anything anyway. So you'll experience that. Okay, and then I'm asking you to use generalized least squares. This is described in our notes, and I'll show you, if I haven't already, the syntax for using it. Briefly, there is a GLS function. GLS is one way to do correlated data regression. The main issue with regression with correlated data is not estimating the coefficients, remember. We don't have to work hard to estimate the coefficients. The challenge is in estimating the standard deviations. So in GLS, let's consider a linear model, y equal x beta plus epsilon. In the ordinary least squares model, ordinary least squares, which for us means IID residuals, independent constant variance. The estimate, maximum likelihood estimate, is what we have seen before, X transpose, X inverse, X transpose, Y. But in the GLS case, let's say GLS, not necessarily IID, the estimate, the MLE, is a little bit different. It's X transpose sigma inverse X inverse, X transpose sigma inverse Y. When we have IID residuals, IID means that the covariance matrix of the residuals just equals a scalar times the identity matrix. So think of this as the general estimate of a regression model. In the IID case, it just happens that those sigmas go away because it boils down to basically just a constant that we're multiplying and dividing by. But when we don't have that IID assumption as reasonable for us, we're stuck. This is the best estimate. This is the MLE. And then the over here on the left, IID case, we saw that the variance of beta hat is sigma squared X transpose X inverse. While in the GLS case, we have that the variance is a little more complicated. So looks like this, X transpose sigma inverse X inverse. Both the estimate and the variance estimates depend on this covariance matrix. So when it comes to actually fitting one of these models, we haven't had to work very hard to fit them in the IID case because all we had to do was look at the design matrix. All of this is just functions of the design matrix and the observed response values. But in the GLS case, we still have design matrix and response that we know, but now we also have this piece that's making our lives harder because it has to be estimated. So I'm going to ask you to use GLS to fit this regression model. This is just a usual linear regression model where we have a covariate for age, we have a categorical covariate for gender, and we're allowing for an interaction. What we do with the GLS syntax is we have to say something about how to handle this capital sigma matrix. And the way we do that is typically we pick from a handful of predefined structures of covariances. So let me pull up our notes real quick to show you what I mean by structures. Here's a handful, or here's 3 commonly used structures for representing that capital sigma. What you would like to do is not have to estimate an entire P by P covariance matrix, all the terms in there. So if we choose a, quote, structure, we can simplify the problem to a smaller number of parameters. For example, we could say that the ijth element of capital sigma is a single correlation, rho, times a single correlation, or a single variance, sigma squared. Compound symmetric would say that the correlation between any two measurements on the same person is equal to rho. And that's the same rho for every person. That's a pretty strong assumption, simplifies capital sigma a lot. A slightly more sophisticated choice would say the correlation between any two time points on the same person is equal to a function of a common rho, and specifically, it's at that rho raised to the power of the difference in times. What that allows to happen is the strength of correlation between measurements on the same person to be higher at time points that are close to each other, and then tail off as you get further away. So my blood pressure right now is highly correlated with my blood pressure in 30 minutes, but using a model like this could be allowed to be less and less correlated with my blood pressure next week or next month. This is also sensible in a spatial context. If you have a spatial orientation of numbers, it is sensible to think that the neighbors to a region, like the direct neighbors, would be more correlated with this location than locations that are far away. That's called an autoregressive model. This specifically is a first order autoregressive model, or in our syntax we'll be calling it AR1. The most flexible choice, nearly most flexible choice, is called unstructured, and this is where we allow every single so every single pair of observations on the same individual to have its own correlation. So my correlation between blood pressure now and 10 minutes is rho 1, say, and my correlation now and blood pressure in an hour is a different rho, totally different, not related by that autoregressive thing, not related in any way, no structure essentially, unstructured. So this is the most flexible choice, but it has a need of a large sample size because it's not simplifying capital sigma for you, which means you have to estimate the full set of parameters. So you would typically need a big sample size to do this. And often, one or the other of these simplifications is sufficient, at least as an approximation. So I'm asking you in the homework to fit a GLS regression model, and GLS is going to ask us, okay, you have correlated data, individuals are tied together by that subject variable or some unique identifier. How do you want to model the correlation? And it will have options for things like unstructured, compound symmetry, AR1. It's actually got more than that, but those are the three we're going to consider in this class. So you will use compound symmetric. Any two observations on the same individual has correlation rho. So we're not allowing for the correlation to decompose over time. We're just saying a pretty strong assumption that the same correlation applies to any pair of observations on the same individual. When you fit the GLS model, the output will include the usual regression output that we're familiar with, estimates of the betas, standard deviations for the betas. It will also show us the estimated correlation parameters. If we do compound symmetry, there's only one correlation parameter, rho, because we're saying rho is the correlation between any two individuals for all individuals. So I'm asking you to pull out the estimate of rho and see if you can manually verify the estimates and the standard errors or standard deviations of the estimates. To do that, you need to get rho, you need to get little sigma squared, and then put it together to get capital sigma. So this requires that you understand what the covariance matrix looks like, specifically when there's this compound symmetry. Let me show you what the covariance matrix looks like. In the orthodont data, we have we have subject, and the first 4 rows are for male 1. MO1, 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 and then we have our response, age, and sex. After those 4 comes MO2, 4 rows for the second male, then MO3, 4 rows, and so on. We have 27 individuals total. N is 27. We might say P, the number of time points, is 4 for every individual. If the data are organized like this, with the first 4 rows are one individual, next 4 rows are another individual, and so on, that capital sigma needs to be 27 times 4 by 27 times 4. So 108 by 108 is what this thing is going to be. But it has what you could call a sparse representation because a lot of the entries in here are 0. Repeated measurements on the same individual we're going to allow to be correlated, but we're still treating our individuals themselves as being independent of each other. So M01 is assumed to be independent from M02 and every other individual. It's within that we have correlation. So what that means about what sigma looks like is it looks like this. Let's say sigma 0, sigma 0, dot, 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 sigma 0, 0, 0, 0. And every one of those pieces is a 4 by 4 matrix. This little sigma 0, according to compound symmetric, is going to be, we can say little sigma squared times a correlation matrix. I don't have room. Let's see. Little sigma 0 looks like this. 1 row, row, row. That's compound symmetry. For any one individual, there's that going on that describes the correlations within observations on that individual. But comparing that individual to any other, there is no correlation. This defines the correlation structure. If we had said AR1, then instead of having row, row, row everywhere, we would have row and maybe row squared, and then row third, row to the third. Row is allowed to decompose as you move away from the diagonal with an AR1 model. And with the unstructured model, we would just have every single one of those rows is potentially its own number. There's no restriction. Part E what I want you to do in part E, the model is distance I is beta 0 plus beta 1 age plus beta 2 gender, beta 3 age times gender. So age is measured in years. Gender is coded, let's see how it's coded. Whenever you have a factor, a categorical variable in R, like sex is, if I say summary orthodont $sex, what it's going to do is in the regression model, it's going to pick the lowest alphanumeric level of this categorical variable to treat as a baseline level. And the other is going to be compared to that baseline level. What that means is for a female who is 12 years old, the model says beta 0 plus 12 beta 1, period. Because gender is coded such that females are 0, males are 1 for sex. For purposes of the model, this is what the model says is the mean distance for a 12-year-old girl. So I'm asking for a confidence interval for that. I'm asking for it in two different ways. One, using matrix or vector operations. This equals some linear combination of the betas, namely 1, 12, 0, 0 betas. And we know that to do a confidence interval, we can say estimate plus or minus a, in the context of regression, a t critical value, say alpha over 2, times a standard deviation of the estimate. My estimate of a female 12-year-old would be beta 0 hat plus 12 beta 1 hat plus or minus this. Or, let me go to another page, same thing would be V transpose beta hat plus or minus T times the SD of our estimate. And we've seen how to do a variance calculation of a constant times a random vector. This right here would equal the square root of V transpose variance of beta hat V. So my interval, based on these calculations, will be V transpose beta hat plus or minus a T critical value times V transpose variance beta hat V. You can pull the beta hats straight out of the summary of the GLS fit. V, you know what it is because I'm asking for a 12-year-old girl. And the variance, again, you know V, this variance of beta hat, you can also get from the output of GLS. I'll see if I can fit in showing you how to do that. But if you say summary of the fit from GLS, one of the elements in there is a variance matrix for the betas, for the beta hats. So you can fit this GLS model, tell it compound symmetric, look at the output, and put the stuff together in this way to get a confidence interval for a particular mean response. The other way I'm going to ask you to do that same thing is with Bootstrap. And I'm asking you to do the kind of Bootstrap that we know how to do, basically. I have previously defined a couple of different ways of bootstrapping regression models. I haven't emphasized that this semester. So to do the Bootstrap to get a confidence interval, all I mean is sample the rows of your data set. Let's see, is that what I mean? Okay, I do need to say something specific here about our data. To do the Bootstrap with correlated data, we need to, we have our data that's organized, like this, 108 by 4. So if we didn't do this, an incorrect way to do this would be to sample with replacement from the rows of this data frame or data matrix. That would be incorrect because after doing that, we would have broken the relationships within the same individual. Because maybe when I bootstrap, I get the first row next to the 8th row, next to the 12th row, or something like that. Which means the first 4 rows now are not the same individual anymore. So if there was correlation between repeated measurements on the same individual, we've lost that information. To bootstrap with correlated data, what you want to do is sample with replacement from the individuals. We have 27 individuals. So a bootstrap routine for these correlated data would look like sample with replacement from the numbers 1 to 27. And then use those numbers to go get the chunks of 4 that correspond to those. So if we sampled with replacement from 1 to 27, suppose we get the numbers 4 and 20 and 8 and then 4 again and ... Then I would go to the 4th chunk of 4. I would go get the 4th individual's block of stuff and put that in my new Bootstrap data frame. So keep in mind, bootstrapping with correlated data, you need to sample chunks within which the correlation lives. So in this case, we're going to sample individuals. As sampled individual, all 4 rows for that individual are brought into the Bootstrap data frame. Another data set is on schizophrenia, and we have a response that is severity of symptoms. Time is measured by week. We also have a treatment variable. So again, make some plots, including spaghetti plots, and then fit another kind of correlated data regression model. GLS does correlated data regression, but it's not the one I would recommend as your go-to choice. GEE has some benefits over GLS. GEE stands for Generalized Estimating Equations, and I'll go through our notes a little bit today to review to say why we like GEE over GLS. So there's a different function. There is a GLS function. Now we're going to use a GEE function. So fit another regression model. Just like GLS, GEE will ask, what do you want to do about the covariances that correlate those correlations? Do you want to pick a specific structure? I'm asking you to try 2 different structures. First, what's called independence. The independence model in GEE says that there is no correlation within an individual. Almost surely an incorrect assumption. But GEE has some nice features that even if you say there's no correlation when you call the function, it, behind the scenes, can still use the data to update or compute more sophisticated standard deviations that are correct. So try GEE starting with the assumption of independence. Also try it with the assumption of, quote, exchangeable correlations. Exchangeable is another word for compound symmetry. Then one more data set, Georgia babies. These are birth weights for 5 babies from the same mother. And the interest is in looking at how does birth weight change from your first child to your 5th child. Here we're going to fit a different type of correlated data regression. This is a random effects model. So in our notes, let's go back to the notes now. There's 2 main ways that I'm recommending you consider doing correlated data regression. GLS is a first step, a crude approach to doing correlated data regression, I would say. These are better. So let's consider either generalized estimating equations, GEE, or random effects models. These are very different in the way that they're represented and in the way that they're estimated. They may have different interpretations, or they may not, depending on the type of data you have. But they are fairly different in what they're doing. GEE is referred to as a marginal analysis, whereas random effects are referred to as a conditional analysis. The reason they're called conditional is that in a random effects model, like on this slide, slide 25, what we say is that the expected value of the response given the random effect or vector of random effects is linear model. So the whole model is a conditional statement. It's response given these random effects. That means our interpretation of the coefficients and the results have to have this given or conditional language involved. Whereas GEE, a marginal model, the previous slide, slide 24, is a direct model of the mean. A marginal model, not conditioning on any random quantities. The mean of Y is linear model. Okay, let me show you an example. I'm going to go get a data set called BVB for Beat the Blues. Under data, let me go to scripts first. Scripts, beattheblues.r, BVB. This is an example of longitudinal data. Okay, so I don't have a data file for these because these also come with a package. Let me see if we have this package on this computer. Library HSAUR. So install. These data are longitudinal from a clinical trial of a multimedia program called Beat the Blues that was designed to be therapy for depressed people. So we had people who are depressed recruited to the trial and then randomized to either a control or the treatment, the multimedia program. Packages here, library, HSAR, and here I'm getting the data. Data, BDB. It's a 100 by 8 matrix. Here's a peek at the first part. Let's see. So we're going to focus on the treatment variable. Treatment as usual means control group. BDB means treatment group. And then these are measurements of depression. So a questionnaire that tries to quantify depression levels. And we have these at multiple time points, or at least we tried to. The clinical trial design was to collect this information 2 months after beginning the study, 4 months, 6 months, 8 months. You can see that there are some individuals who dropped out. So this person, for example, was in the treatment group, came in with a baseline depression number of 26. After 2 months, came in and had a 23, and then dropped off the map. Notice also that these data are organized differently than the orthodont data. Both of them are longitudinal data, but they're organized differently. The orthodont data had separate rows for every single measurement. And then we had to have that subject variable to tie the rows together that are in the same individual. This kind of format is called the long format, as in you've stretched the data out separate rows for every single observation. This format is different because every individual only shows up in one row, and we just have all their repeat measurements as separate columns. This is called the wide format. When you have correlated or longitudinal data, sometimes it'll be one way, sometimes it'll be the other. You need to recognize the different types, and you need to be able to go back and forth because different functions require different structure types. In order to use GEE, the data is expected to be in long form. So the first little chunk of code here, I'm going to translate from that wide format to long format. Instead of one row for every individual, let's do separate rows for every observation, and then we'll have to create a variable that keeps track of the individuals. The good news is there's a function that does that for you called reshape. So here is beat the blues underscore long form equals reshape the wide form. Let's create an identifying variable called subject. I tell it the columns that specify to repeat measurements over time. And I tell it the direction I want to go. So I'm going from wide to long. Now we have Beat the Blues long 400 by 7. And it looks like this now. Subject 1 at the first time point. Subject 2 at the first time point, and so on. GEE, the R function GEE, expects the individuals to be ordered in clumps, like they are in the orthodont data, with the first 4 rows being individual 1, followed by the next 4 for individual 2. We don't have that after having done reshape, so we've got just a little bit more to do. What did I just do? Oh, I'm just illustrating what I just said. I'm only looking at the first 3 individuals, and you can see that the data are organized with individual 1. Their measurements are spread out over these different rows. We need to reorganize a little bit further. So here's how I did it. I ordered the subjects. So that will put all the subject 1s at the first, followed by all the subject 2s, subject 3s, and so on. And then reorder the rows according to that. Now we have the data organized like we want. 4 rows for subject 1, followed by 4 rows for subject 2, and so on. These are ready to be thrown into GEE. I bet I don't have the package. Let me get it real quick and show you just what the output of GEE looks like. The reason we care about this GEE and random effects models stuff is because if we were to do usual linear regression to fit this model, we would get the wrong standard deviations of the coefficients. So I just fit 2 GEE models. Let me look at one of them in detail. Summary. Here's the usual regression output with a little bit of extra detail. If you were to do IID regression, you would get what are called naive standard errors. Standard errors that do not account for the correlation over time. What GEE gives us that's so valuable are correct standard errors. Standard errors that have incorporated the correlation structure that we chose. Notice that the standard errors tended in this case to be bigger than the naive ones. So if we had done usual linear regression with these data, we would have had anti-conservative inference. Our p-values would have been bigger, smaller than they should have. Our confidence intervals would have been tighter than they should have. Okay, we are out of time. We're going to spend at least a week on correlated data, so I'll go through this in a variety of ways with several example data sets. We have several example correlated data scripts that you can look at. But this is at least code that you could start playing with in your homework to do the GEE part. I'll show you how to do random effects next week. Questions? Okay. Yes?
The last video you have a script with GEBB. I can't find the script.
I pulled it off because it's in your homework now. Your third problem, okay, the question was GA babies was in the video I posted, but it's not online. And that's because I pulled that script off, and I'm going to ask you to do some of it yourself. So you can watch me on the video do some of it, and then do this yourself. Okay, have a good weekend.